move on to our last paper, which is going to be presented by Lu Han. It's called Cool Cities, the Value of Green Infrastructure. Lu, you have 30 minutes.
So first of all, I want to thanks to everyone for staying until this very last talk, and also particularly those people in the US time zones. And also I would like to thank the organizer for including me in this wonderful program. I really wish I could see all of you in person in Singapore, because Singapore is one of my favorite countries. Singapore is called Garden City, and in Asia, it's probably the greenest city. And even around the world, it's probably one of the very few top greenest cities. As you can see from my background here, I feel very connected to those green infrastructures. And this is because my grandpa was a forestry professor. So he got his PhD in Germany and then went back to China afterwards. So his entire career is about trees. Now, as his granddaughter and also as an urban economist now, one thing that I have been thinking about is what do those trees mean for cities? So this paper really is my first attempt to try to address this question. And it's joint work with Stephan Heblich from Toronto, Chris Timmins from Duke, and Yanos Zylberberg from Bristol. Compared to the previous 3 papers in the program, this work is still like an ongoing project. So your feedback would be very much appreciated. Okay, so in North America, we know that 82% of population live in urban areas. And in Singapore, this number is about 100%. So as much as many of us enjoy living in the urban centers, this high density-based urban living does impose a lot of stress on our local natural ecosystems, such as traffic noise, air pollution, and also the social stress, and particularly the so-called urban heat island effect, which refers to much higher temperature in the urban center relative to our rural surrounding areas. Now, fortunately, in the urban areas, you see not only building and people, but also those green infrastructure. And from the literature, what we have learned is that the trees are there. They're not just providing gorgeous views. They also connect us much better with our natural ecosystems. For example, there has been this concerns about urban heat island effects, but in the summer, trees will provide you with very nice cool shades. And in the winter, trees would help to block all these strong winds. So potentially it can generate a lot of energy consumption savings for the residential households. On top of that, the trees can also help to improve air quality, to help reduce traffic noise. And if you live on a leafy street, those trees will help to promote your physical activities, make you feel mentally more relaxed, happier, and live longer. Now, those type of services and benefits that trees provide for local communities, they're essential for a more green, more sustainable, and a more climate resilient type of urban living. Recognizing all these social, ecological, and economic benefits of urban trees, we now see cities around the world, they're setting up their urban tree canopy goals for the next decade. In New York City, they're aiming to increase the tree canopy to 30%. At Madison, Toronto, and Baltimore, we are aiming at 40%. Annapolis is aiming at 50%, and Pittsburgh is aiming at 60%. Singapore currently has 7 million trees, but with this newly released Singapore 2030 Green Plan, the country is going to plant another 1 million trees in the next decade. Now, a lot of these tree canopy goals, they are very much related to the policy initiatives dealing with climate change. But in the same time, we also realize that growing more trees and even just maintaining the current tree canopy can be very costly in urban areas because land is very expensive. So this begs a very important question, which is, can we quantify those economic and particularly the ecological benefits of urban trees? In this paper, we're trying to address this question by estimating, the relationship between the urban trees and also the energy consumption and property values. So our focus is Toronto. Toronto is one of the greenest cities in North America. In 2018, it has 12 million trees, more than the combined number of trees from New York City and from Los Angeles. However, quantifying the benefits of those urban trees can be very difficult. Now, as economists, we see three challenges right away. First of all, as we all know, leafy streets, they tend to be in well-established neighborhoods, and therefore, they may have a better school districts, they have a better homes, they have a more wealthy families, and all of this can introduce this omitted variation bias. In addition, we know that people who choose to live in a green environment, well, they naturally would be more concerned about the environment, and they would choose to consume less energy than the average household. So this is a selection issue. On the top of that, there's also reverse causality. As we said, in the rich neighborhoods, the land cost is also very high. So that makes the opportunity cost of growing trees very high, which makes it more difficult to grow more trees. Now, how do we deal with all these empirical challenges? Well, in this paper, we're going to exploit two sources of exogenous variations. First of all, to quantify the amenity value of urban trees, we're going to exploit this natural catastrophe, specifically this so-called emerald ash borer infestation, which wiped out 8% of the tree canopy from the city of Toronto. In addition to quantify these ecological benefits of the urban trees on residential energy consumptions, we're going to exploit these short-term fluctuations in the temperature between extreme weather episodes interact with the position of trees surrounding the house, and also solar angle and wind directions. So now let me show you the data. So what you see here is a map for the city of Toronto, and here is a spatial distribution of intensity of housing transactions between 2007 and 2017. For each transaction, we observe the property address, the transaction date, the transaction price, the detailed house characteristics, and also neighborhood level characteristics such as income and also local urban infrastructure. Now, in this map, what you see here is the spatial distribution of urban tree canopies at the neighborhood level and also the neighborhood income level. So the shades of color indicates the percentage of tree shades. The size of a circle indicates the neighborhood level income. As you can see, even in Toronto, a green city, these tree shades have become increasingly an equity issue. In a hot summer, if you walk in one of the rich neighborhoods such as Forest Hill right here, you're going to get a lot more sunshades than if you walk in a low income and marginalized neighborhoods. Now, in the literature, those tree shades are typically measured at the neighborhood level. Here, we are interested in the property level. So to do that, we're going to rely on these high-resolution satellite images the City of Toronto has taken in various years. Particularly, the Urban Forestry Department has recently developed these high-resolution land classifications and implemented them on the 2008 and 2018 satellite images. For the first time, this generates a very accurate information of spatial distribution of the tree canopies across the entire Toronto area with a resolution to the property level. So what you see here is a snapshot of a part of Toronto, and as you can see, dark green indicates trees, light green indicates grass, red is the buildings, brown is the road, and the sand color indicates other hard surface. So for each property here, we're interested in its exposure to the trees relative to versus to other green components such as grass. So to do that, for each property, we generate this discrete number of individual trees within 50 meters from the property's centroid in each year. And that number of trees within 50 meters is going to be the key variable of interest in our hedonic exercise. So here, what you see is a summary statistics of our house characteristics and tree characteristics. In particular, on the right, as you can see, I grouped all the transactions into the properties with above median tree density and properties with below median tree densities. And as you can see, for houses on the leafy streets, on average, they have 6 times more trees, but also they have 10% higher house price. Now, this 10% is not entirely due to the tree premium, because if you look at the property characteristics, you can see, the properties on the leafy streets, they're also larger in size, and on average, they have 1 additional room. So this does suggest that, the properties with a lot of trees surrounding them, they can differ from other houses in a systematic way, sometimes along those observed dimensions, and sometimes maybe along those unobserved dimensions, which is going to cause this omitted variable bias. Now, in this slide, we are going to plot the relationship between the number of trees surrounding each property and their transaction price. And as you can see, for most of the range of price segments, there is a strong positive relationship, indicates that, houses on leafy streets, they tend to have high price. But as we said earlier, this positive relationship is contaminated by this omitted variable bias. Also, as you can see, as we get to higher and higher range price segments, this positive relationship gets flatter and flatter and even reversed in some range. And this indicates this reverse causality concern, meaning that in those expensive neighborhoods, land value is high, and therefore the cost of growing more trees is also high. So how do we deal with all these identification issues? Now let me introduce you to our identification solution, which is this green beetle here. Now, this green beetle is called emerald ash borer. It's emerald because it's green. It's ash borer because it's an enemy for all the ash trees. Once it gets on an ash tree, it takes 1 to 4 years for the tree to die. So emerald ash borer was first accidentally introduced into North America in early 2000s. And in fact, it was first detected in Michigan and quickly spread over to the east, to the south, to the Midwest, and to the north, including Canada. And here is where Toronto is. In the US, the emerald ash borer has already killed over 12 million ash trees. In Toronto, emerald ash borer was first detected in 2007, and within 10 years, it has already killed nearly all of 860,000 ash trees, which accounts for 8% of the tree canopy in Toronto. Now, from the city of Toronto, we obtained the register of all the public trees, including, tree species, which allow us to identify which tree is ash tree, a tree address, which allow us to identify where those ash trees are. And in fact, as you can see here, ash trees are everywhere, but they're particularly concentrated in the north, in the east, and along the lake from here. Now, we also observe the tree size, which allow us to construct this tree canopy, which is going to help us to construct the shading potential later. Now, in the same time, we also observe the date each tree receives this tree azine injection, which is meant to deal with this EAB, and also the date when the tree was finally removed from the street. Now, emerald ash borer was a very unfortunate disaster for the urban forestry, but fortunately for us, it presents a very nice identification solution because it creates this exogenous variation in the secular evolution of the tree canopies, which is independent of the neighborhood level price dynamics. So that's going to help us to recover, the causal effects of urban trees on the property values. To show you how this works, let me take you to our hedonic exercise. So for each transaction, we regress the property price on a set of rich time-varying house characteristics and neighborhood characteristics, including number of public trees, initial tree coverage, neighborhood fixed effects, all interact with year fixed effects. By doing so, we can flexibly, allow for this differential neighborhood evolution in terms of price dynamics, and also we can allow for those time-varying premium to the different house characteristics. The variable of interest here, of course, is the number of trees within 50 meters. But that variable, as we said earlier, is endogenous for many reasons. So here we are going to instrument this variable with the number of ash trees at the postcode and the yearly level. And the idea is we are going to create these exogenous variations in the tree canopy derived from this EAB infestation. Now, in Toronto, this emerald ash borer was first detected in 2007, and the city started, ordering to remove those trees in 2011. So in our estimation, we look at the pre-treatment period, which is 2007 to 2009. Around that time, EAB was not publicly known yet, and Toronto has not really lost any ash trees yet. We compare that with the post-treatment period, which is 2015 to 2017, and by then, this is public knowledge, and most of the ash trees have either died or removed, from the street. So now let me show you our estimates here. As you can see in column 1 and column 3, we simply run OLS estimation without and with a rich set of controls. But in both cases, you can see the conditional correlation between the number of trees and the transaction price is small and insignificant. So in column 2 and 4, we now instrument the number of trees with the number of ash trees. And as you can see, the first stage power is very strong. And when we look at the second stage in both specifications, we see the tree premium here is positive and substantial. In particular, when we look at the last column here, where we included all the controls, as you can see, else equal, if you have one tree within 50 meters from the centroid of your property, it's going to improve your property value by 1.2%. So in Toronto, the average home value is about $1 million Canadian dollars. 1.2% means about $120,000. That's a substantial tree premium. We also experimented with different distance rings, 30 meters, 20 meters, 10 meters, and we do not find much variation in this estimate. But of course, for you to take our estimate seriously, I have to convince you about our identification assumption. Well, the assumption here is that the initial allocation of ash tree is orthogonal to the evolution of these residential prices at the postcode level, conditional on all the number of public trees and all the other things we have included. Now, this raises a question, which is what determines the initial spatial distribution of the ash trees? Well, it turns out the spatial distribution of the ash trees was inherited from the earlier spatial distribution of elm trees, which used to be considered as the first best urban trees in North America. But elm trees, unfortunately, were killed or were removed in a previous big-scale infestation, which is called Dutch elm disease. Many of you probably have heard of that. Now, Dutch elm disease started in 1930s and spread until 1970s, and removed many of the elm trees from many cities in North America. So those cities decided to replace the elm trees with ash trees. And in Toronto, this replacement occurred around 1930s. So to the extent you think that initial allocation of ash trees is going to reflect the urban developments in the 1930s, and to the extent that you think that's going to have some implications for the subsequent neighborhood price dynamics, then this assumption might be questionable. So to see whether this is the case, we're going to basically repeat the same IV estimation we have done for two placebo periods, which is 2007 to 2008 and also 2009 to 2010. And the idea is if that initial spatial distribution of ash trees is going to affect house price dynamics, we are going to see significant correlation here. But this is not the case, suggesting that this is less likely to be a concern. So hopefully by now, I can convince you that those urban forestry does contribute to a significant positive, amenity value as high as 1.2% of the property value. Now, the next question, and I think an even more interesting question, is what contributes to that amenity value? Now, at the beginning of the talk, I have mentioned many benefits a tree provides. Given all this, climate change concerns, we are particularly interested in this mitigating role that urban forestry has played in terms of, adjusting, cooling down the cities in the summer and also block winds in the winter time. So we're going to start with this cooling effects of urban forestry. Now, just to give you some idea, this is a neighborhood in Toronto called South Parkdale. And in this South Parkdale, sorry, let me try to see whether I could use I lost my mouse here. Okay, so here we are. So in this South Parkdale neighborhood, you can see this street is called Dufferin Street. It's one of the main streets in Toronto. To the west of Dufferin, there are a lot more trees than to the east of Dufferin. And correspondingly, when you look at the summer temperature between June 1st, 2018 and September 15, 2018, you can see the west of Dufferin enjoys much cooler temperature to the east of Dufferin, even though the two neighborhoods are adjacent to each other. Now, to make this relationship more formalized, I'm going to plot the relationship between the neighborhood temperature and also the tree coverage. So as you can see, the vertical axis here, this is average tree shades in the neighborhood. And in the horizontal axis here, this is the average temperature in the summer of 2018. There is very strong negative relationship here. And in fact, if you move from a neighborhood with 5% of tree shades to a neighborhood with 10% of tree shades, you are going to enjoy 2 to 3 reduction in Celsius degree reduction in the summer temperature. Now, what does that mean for a residential home? Well, for the residential home, it means that if you have a tree surrounding your house, that tree is going to block much of the sunlight from reaching the ground and the building, which imply potentially, big consumption savings in the cooling expenses. Now, to see whether this is the case in our data, basically, we for each property in our data and for at any particular point of time, we check the solar angle as implied by the particular time of the day of the week of the year. And then we select all the trees in that direction within the distance d from the properties. And we impute the fraction of the property that is covered by the trees, taking into account the house size, the tree size, and the distance between the two. And then we integrate that hourly shading potential to the weekly shading potential and to the whole postal code level shading potential. Similarly, in the winter time, we recognize that trees are going to help to block the winds. So we construct this wind sheltering potential by taking into account the wind speed, wind direction as implied by a particular time of the year, and also the position of the trees relative to the house, and also the distance between the two. So with that, what we want to do is to estimate the energy consumption savings generated by this, shading potential and sheltering potential. And for that, we need the energy consumption data. So our energy consumption data comes from Toronto Hydro, which provides all these electricity bills for all the households in the city of Toronto between 2011 and 2015. The billing cycle is between 1 and 2 months. And using that, we calculate households' average daily energy consumption and then predict weekly average energy consumption in each postal code in each week, controlling for household fixed effects and house fixed effects. So now we are ready to estimate these energy consumptions generated from urban forestry, and we are going to start from the cooling effects. So we are going to first restrict our sample to the summers, which is in Toronto is between May and September. And then we are going to regress this log weekly postal code level energy consumption on a dynamic variable called heat wave that indicates whether the temperature falls within the top decile recorded in that summer, and the interaction of that heat wave with this solar shading potential, controlling for a bunch of interactions of fixed effects. So here I want to show you our estimates. In particular, I want to focus on column 3, where we have the richest controls here. So as you can see, the dependent variable is energy consumption. During the summertime, you can see during the heat wave period, the households are going to increase their energy consumption by 4%. And presumably that's because of more intensive use of air conditioners. But if you have 10 percentage point increase in the tree coverage, in the tree coverage surrounding your property, then you can reduce your summer heating expenses by 3%. And in particular, if you look at during a heat wave time, that 10 percentage point increase in the tree shades is going to reduce your energy consumption by 5.6%. Now, just to give you some idea, in Toronto, my summer energy bill is about $100. So 3 to 6% of $100 may not really mean much. But if you multiply that by the number of households in the entire GTA area, well, that means a 10 percentage point increase in the tree shades is going to generate $25 million annual savings in the cooling expenses alone. And that is substantial. Now, I want to say that the tree benefits are not just limited to the summer. In the winter time, we also see tree help to block the winds and therefore help us to save on heating expenses. So here we repeated similar estimation for the winter time. And as you can see, during the winter, with 10-degree reduction in the wind chill equivalent temperature, which is about 1 standard deviation, your energy bills, your heating expenses is going to increase by 3.7%. However, if your house is sheltered by the trees, then that heating expenses is going to reduce by 40%. And I also want to say, this number actually looks smaller compared to our cooling expenses. But in the same time, our data here is only based on electricity energy bills. In Toronto and probably elsewhere, a more popular energy source for the heating expenses actually comes from natural gas. So in that sense, our estimates for the heating expenses actually is a lower bound. But fortunately, just last month, we have finally obtained this natural gas data from Toronto Enbridge, which means that next time, if I have a chance to present this work again, we'll be able to give you a full estimate of these energy consumptions for both electricity bills and natural gas. Now, I also want to show you, just with our current estimates, how this estimated energy consumption savings is going to vary with the position of the trees relative to your property. So on the horizontal axis here, this is the position of trees relative to your house in the north, west, south, and east. On the vertical axis here, this is estimated cooling expenses during the heat wave period in the summer. As you can see, having a tree in all directions of your property is going to generate substantial savings in the cooling expenses, but particularly so in the south and in the east, where savings is about 9 to 11%. Why so much stronger in the south and in the east? Well, because sunlight mostly in the summer comes from the south and east, so the trees are going to provide a stronger shading effect when they block the sun. And on the right panel, what you see here is how the heating expenses in the winter varies with the positions of trees. And as you can see, having a tree in all three directions, north, west, and south, is all going to give you substantial saving there, but particularly so in the north, and almost no saving at all if you have a tree to the east of your property. And that's because, in Toronto, the winter winds mostly blows from north, sometimes from west, sometimes from south, but rarely from the east. Okay, so with that, I want to say, I want to conclude by saying that, in this paper, using these large quasi-experimental variations derived from this natural catastrophe, we find a substantial, amenity value that urban trees provide for the local properties. And out of this 1.2% of hedonic property tree premium, based on our back-of-envelope calculation, we find that the energy consumption saving effects accounts for 20% of that tree premium, suggesting, that there are many other benefits the tree has provided, which are also valued by households. I also want to mention that in the US, residential cooling and heating expenses account for 11% of the total energy use. So our estimated energy consumption effects from the urban forestry could have important implications for the future energy use. Going forward, as I mentioned, this is a still ongoing project. What we plan to do is to quantify those heterogeneous impact of the trees across different neighborhoods with different social demographics. Now, at the very beginning of this talk, probably the slide you didn't get to see, is that I showed you that around the world, many cities have set their, tree canopy goals, including Singapore. But from welfare perspective, it's not just how many more trees we need to plant. It's also about where to plant those trees. From the city of Toronto map, you can see, there's a huge variations across different neighborhoods in terms of tree coverage, right? You can see the rich neighborhoods here have 60% tree shades, but the poor neighborhoods here, like only less than 10% tree shades. And that means rich people are getting richer, not only in their accumulated wealth, but also in the benefits and in their access to the public assets, right? So a lot of benefits we mentioned earlier in this paper, such as reduced energy consumption savings, mitigated the extreme temperatures, and also including improve the air quality, and it's just improving this neighborhood character, most of this is going to be enjoyed by rich people, and low-income people are not going to be able to enjoy much of this. And we know that trees, at least public trees, they're public assets, and therefore it is upon the city policymaker to determine how they can distribute these public assets along the streets, along the public park, along the public space in a more equitable way. And in that sense, I hope that our estimates of a heterogeneous impact of tree shades across different neighborhoods with different social demographics could serve for that purpose. So I'm going to stop here, but I want to just mention that, thank you.
The discussant is Yu Quinn from NUS.
So thanks a lot, Lou, for the great presentation. I'm always a big fan of your research. And since you mentioned Singapore, maybe before I start my discussion, I want to show you this picture here. This is actually a new building at NUS. It's an award-winning building. It's called Net Zero Energy Building. And you see there is a tree in front of the door. And after reading our paper, now I think I understand why this is an award-winning building. Just to give you a summary of the paper first, I think this is a very cool paper on the value of urban trees. And it has a very nice research design relying on two exogenous variations. The first one is the EAB infestation, which is to identify the causal impact of tree densities on housing prices. And the second variation is the short-run weather fluctuations and the position of the trees, which is to identify the association between tree density, tree positions, and the energy consumption. So I think there are two main findings in the paper. The first is the tree premium. One additional tree within a range of 50 meters from the house increases the property prices by about 1.2%, which is really a big number in terms of the economic magnitude. And the second is there is substantial energy savings from urban trees. So I think, after reading this paper, I was thinking, why is there a tree premium? So I think the first possibility is the mechanism extensively discussed in Lou's paper, which is the energy savings, because of the solar shading potential and the wind sheltering potential of the trees. But I'm thinking whether it is always energy savings, because in the summer, I understand solar shading could reduce energy consumption, but in the winter, solar shading may increase energy consumption, right? So I think maybe it's worth to explore more for the data in the winter, and also given in Toronto there's a very long winter, so this may represent a very important portion of the energy bill across the years. And also, even I understand this energy savings mechanism is valid, but the effect is relatively small, given there is a 1.2% tree premium in terms of the housing prices. So I think if this paper wants to sell this 1.2%, maybe it's also important to explore other mechanisms going on. And I think another possibility could be due to the aesthetic value of the trees in terms of the adding the beauty to the houses. I think it's really hard to verify this mechanism. But what I was proposing here is maybe there could be some heterogeneity across different individuals. For example, I know that according to the feng shui theory in China, some superstitious people in China actually believe in the theory, and they actually dislike trees because having a tree near the front door of the house is an undesirable feature because it prevents the sunlight coming into the room. So I think you have the information regarding the position of the trees, and I'm not sure if you have the ethnicity of the homeowners. If you have, maybe you can test this alternative story. And there could be other benefits that contributes to this tree premium, such as the noise reduction function of the trees, or as Lou mentioned, having a tree may relieve the mental stress of the homeowners. And finally, it could also be due to omitted variable bias, and Lou also discussed about this point, and that's why they use an IB strategy to as a research design to address this omitted variable bias problem. So I think I have 3 comments on this paper. The first is regarding the estimated price premium of the trees, the 1.2%. I think I have 2 concerns. The first is the difference between the OLS estimation and the IV estimation. So actually in the OLS estimation, you almost get a kind of a precisely 0 effect, but in the IV estimation, you get a large and significant effect. So maybe you want to explain more about why there is a difference in terms of the estimated magnitude and significance. And second, I find actually in your different tables, there is a large variation in terms of the estimated magnitude of the tree price premium using your instrumental variable. Actually, this 1.2%, it seems to be a lower bound of your estimates. In your table 3, you actually have estimates that is almost like 10%, which is a bit too much, which is a bit too large for me. So I think maybe you want to explain more about this variation in magnitude. The second comment is regarding the research design. So I understand you have the tree data for 2 years, but your property transaction data is actually annually for more than 10 years. So I'm thinking about whether you can conduct a robustness check to only use the 2 years of transaction data to match with your tree data. Because I understand that you assign the tree density values based on an arbitrary year cutoff. So maybe only using 2 years of the transaction data can reduce some kind of measurement error going on for this analysis. And also, alternatively, I'm not sure if you can run a diff to as another robustness check, because I definitely see a research design there where the treatment could be the houses surrounded by the ash trees, subject to the EAB infestation, and the control group could be houses surrounded by other trees. And also, I'm not sure if you can run an event study, because you mentioned in the paper that you have access to a specific register recording the dates of the EAB removals. So if you can match that date with the transaction records, you can actually conduct event study to see whether the price declines after the removal of the trees. And my third comment is regarding the energy consumption. So I understand that you measure the extreme temperature using a dummy called heat waves. But I think in the environmental economics literature, people also use temperature bins in the regressions instead of a single dummy. So usually they set up like 3 degrees Celsius bins and use maybe 12 to 15 Celsius degree as the most comfortable temperature bin. And all the effects of other temperature bins are compared to this most comfortable temperature bin. That's the way that people deal with this regression if they have daily data. But if you have monthly data, I'm not sure if your bills are monthly or not. You can also use the number of extreme weather days to measure the extreme temperature. So maybe that's worth another robustness check. And also, I think you need to control for other weather variables in the equation, which may also affect energy consumption, such as rainfalls, humidity, visibility, wind direction, etc. So I assume there is a spatial variation in terms of the weather within Toronto. Otherwise, I think those variables are already captured in the time 6 effect. And finally, I'm still wondering whether you can further explore the effect in the winter, because it seems like the wind shattering effect and the solar shading effect are in different directions. So the overall effect is kind of ambiguous. So I also want to discuss a little bit more about the potential contribution of this paper, because I think this is a very interesting paper which could make a contribution to the climate change literature. Because in the climate change literature, people always discuss about adaptation to climate change. And they always mention, people should use more air conditioners to adapt to climate change. But actually, based on your finding, you're actually suggesting if people have trees near their house, it could serve as a substitute for air conditioners. But also, like the environmental scientists always believe, planting trees is not a substitute for reducing ongoing greenhouse gas emissions, because trees can only have limited capacity to capture the carbon in the air. But I think your discussion on the energy saving effect of trees could be new to this climate change literature. Well, I see this idea has been discussed in some building and environmental papers, but without rigorous statistical analysis, such as the paper that I found last night, this ecological economics paper. They studied the same question, but with only 160 households, and you have more than 800,000 households. So definitely there should be a contribution there. And I think, in addition to the energy savings in terms of the monetary values, you can also calculate the energy consumption savings in terms of the greenhouse gas emissions. And I think if you have this calculation, you can also try to expand the discussion by comparing this calculation across different countries, because this calculated number definitely depends on the electricity structure of the country. In Canada, actually, Canada is one of the countries that have a very high penetration rate of renewable energies. So the calculation on GHG emission in terms of this energy savings by trees could be relatively lower compared to other countries who still rely on fossil fuels, such as China. So I think if you want to sell your paper to the climate change literature, maybe it's worth to discuss about these cross-country differences. And also, I think your paper could contribute to the energy consumption literature, because in this literature, people always thinking about the effects of different instruments on reducing energy use, such as prices, rebates, or information nudges. But actually, your paper is saying that green infrastructure help to reduce energy consumption. And I think if you want to sell to this literature, you can further test whether there is a rebound effect. So for example, whether this effect diminishes over time, or actually people increases their energy consumption in those non-extreme weather days. So these are the things that you can further explore if you want to make more contribution to the environmental literature. I also pointed out some minor issues, but I don't want to waste the time discussing here. I will send you the slides later on. So overall, I think this is a very interesting and promising research, and all the best with publishing it. Thank you so much.
Thank you, Yu. You want to take a couple of minutes, Lou, to respond?
Yes, thank you. I really want to thank you for your time and for your comments. Please do send me your slides. And I also want to apologize, our writing at this stage is still very preliminary. So I really thank you for giving us the detailed comments based on our current draft. Just a few points. First of all, you talk about, the summer and the winter effects. They're in different directions. And in fact, I think they're in the same direction, which is having trees is going to reduce your heating expenses. Is also going to reduce your cooling expenses. So having trees are actually going to be winner and winner both for the summer and for the winter. And for the magnitude wise, I do agree when we experiment with the different distance bands, we do see larger effects when you get to the smaller distance rings, for example, 10 meters. However, the estimate there gets less precise. It has larger standard error because there are fewer tree observations there. So that's why, we didn't go there. You also mentioned about this yes, using the annual data instead of a 2 year and 2 year before and 2 year after. We do agree with that. And in our robustness check, we are doing sort of an annual data like check. But the reason we choose this as a baseline specification is because we think there is a uncertainty about the timing of those trees. So once emerald ash borer becomes the public knowledge, people are going to realize that they are going to lose these trees sometime down the road. So the value of the property should capitalize all these future loss of the ash trees. So that's why we consider 2011 as a sort of cutoff, because that's the time when city order to remove the trees. And then yes, I think the energy consumption, the winter effect is particularly interesting. I do agree with that. And actually, I think winter's effect is going to be larger than the summer effect. So that's why we tried very hard to get natural gas data. And the point that you made about the different countries have a very different sort of energy consumption, like the structure in terms of sources they're using. I think that's an excellent point. We do want to understand how Canada is different from other countries in that regard. So overall, thank you so much for your very helpful feedback, and please do send me your slides and I will follow up with you offline. Thanks.
Thank you.
I had one quick question, Lou, which actually follows up on something that you was talking about, which is, if you have a lot of shade cover, that makes installation of solar panels on your roof potentially, less valuable or less possible, just because there's just less sunlight coming through. So is that potentially an offset here that we need to worry about?
The solar shading potential, yes, I do think so. I don't have a good answer to that question at the moment. I think, we also want to see sort of like the different type of the roof material and how they are reacted to that. So maybe we'll do some follow-up work on that.
Great. Well, we're just about out of time. If there's no further questions, let me open it up for one last possibility for questions.
Yes, just if we have a minute, I would like to ask Lou to what extent you guys could measure redistributional effects that might not be captured on prices, in the sense that those that may have the trees nearby in the vicinity, they definitely could get some of the benefits in the summer and the winter, but the other taxpayers are, taking care of the maintenance throughout. So the question is, are the prices kind of fully capitalizing what would be, the cost of, maintaining it, or there's some surplus that, it's retained by those that enjoy the trees, that they really doesn't get priced in? Do you guys have any sense to what extent, in that positive externality, there's a lot of surplus left on the...
Yeah, that's an excellent question too. So right now we do not have much information about the maintenance cost, and I think you bring up a very good point, and that's something we want to understand. And I think you do raise an important thing, which is we want to understand sort of aggregate willingness to pay by the local neighborhood, taking into account all these externalities. Right now, the number of trees we considered are, some of them are public trees, some of them are private trees. So public trees, that burden is going to fall on the city, and the private trees is going to fall on the specific individual homeowners. And this could have positive externalities for your neighbors, because tree effects, cooling effects in particular, has to sort of cross a certain threshold in order for that temperature to really cool down. But it could also have negative externalities, like maintenance of like falling leaves on your neighbors. So that part is that externality. You're right. I think it's something that we want to look into in the future. Maybe we can exploit the distance to the neighbors, and see how the different neighbors are willing to pay for the different trees. Yeah, thank you.
Thank you.